Hello, everyone. This is Maxime Flament from 5G Automotive Association. I'm very happy to welcome you to this webinar on integrated sensing and communication for C-V2X, where we are going to cover topics like use cases and technology features. So we have quite a heavy agenda, but before I go through the agenda, I would like to say that the presentation will be shared to all participants and posted on the 5GA website. Also, the recording of this session will be also accessible to all the participants. And we will have also a Q&A session at the end. So while the speakers are giving their presentation, don't hesitate to post your question on the Q&A button there. And these questions are facilitated by the 5GA Secretariat. We will then curate them, and then I will try to cover the most relevant ones if there are too many questions. As an introduction, this is organized by 5GA. This is an activity that is quite long-term with regards to our work program, very relevant. But why do we care so much about connectivity for automotive? Actually, connectivity is really something that is everywhere in the product planning of the vehicle manufacturers. In the currently and in the next future, you're going to have connectivity everywhere in the cars in the different regions of the world. This is truly a global activity, so that means that we need to have a global viewpoint on connectivity and how we embed it into our cars. But at the same time, there are regional flavors that need to be taken into account in China, US, Europe, Korea, Japan. And 5GA is actually one of the major associations that is looking at this from a global but also regional aspects. So our mission is to align the global stakeholders and foster and initiate future connectivity solutions. Let's go to the next slide. And in a nutshell, the 5GA is a place where the telco industry and the automotive industry are meeting. They are discussing end-to-end connectivity needs. They are making sure that connectivity needs are reflected in the standards, and eventually also looking at where are the market entry barriers in terms of the connectivity in the different regions of the world. Next slide. We are a truly global cross-industry association. We represent 10 of the top 15 OEMs, 8 of the top 10 MNOs, and 2 of the top smartphone vendors. Today, we are 115 members from all over the world, representing the whole ecosystem. And perhaps that's one of the last slides. Next slide. I'll go dive directly towards the real agenda of this meeting. Can I get the slide back? So this sorry. No, well, we'll dive into the objective scope first with Jose Zelaya from Huawei, and Jose, you have the floor now. Thanks.
Thank you very much, Maxime. So hello, everybody. My name is Jose Perdomo Zelaya, and I'm the lead of the 5GA work item on ISAC, Integrated Sensing and Communication. And yes, as you saw before from the explanation from Maxime, we have been up until now mostly focused on connectivity requirements from the 5GA scope. But now with this new work item ISAC that we started a couple of years ago, we introduced the sensing service level requirements in the C-V2X ecosystem. So before I dive deep in the outcomes of the work item, I would like to firstly, let's say, define what is ISAC for automotive. So integrated sensing communication in the C-V2X context, it means that we integrate the sensing functionality into 3GPP communication systems. These communication systems are implemented in infrastructure, either base stations or roadside units, as well as automotive vehicles and all other types of vehicles as well at different levels. We're going to describe the different levels in the subsequent slides. And this integration can be done by sharing resources, hardware, or common signals over the air for both the operation of communication and sensing. And why ISAC for the C-V2X ecosystem? So ISAC is not expected to replace conventional, let's say, state-of-the-art automotive sensing systems that are already deployed, but rather complement and improve the sensing functions and as well the connectivity functions. So in cabin and environment perception, by having ISAC sensing either as an extra source of sensing information or complement the already deployed automotive systems, we can improve the overall perception for meeting the C-V2X use cases. And as well, we can use this sensing information derived by the 3PP system to improve wireless connectivity. So this directly related to realizing the 5G use cases. And an overarching benefit of potential benefit of having ISAC in C-V2X is the potential for hardware use in constrained form factors. So using the same hardware to perform both functions, which this can be very attractive from both space and sustainability and so forth. So maybe this picture can dive more deep into what is ISAC for us. So for example, in the left one, we see a side link communication in which you have in the blue line, the communication frequency band. In the green line, we have the sensing frequency band, which would use some non-3GPP sensing. And ISAC means this is just one example of integration that you use both functions in both bands, either multiplexed in the time domain, for example, or some other way. And then we have the example of V2N communications, having a communication in one frequency band with a base station and doing the sensing. This is usually the case. And then this in one level of integration, then we have some coordination of both systems, infrastructure, and vehicle to perform the communication in the same band and multiplexed in some way in order for the signals to be orthogonal. So in the context of the intelligent transportation system is that, okay, with ISAC, we will estimate the position, orientation, and velocity of traffic participants, and as well other dynamic environmental objects that are relevant for the safety or comfort use cases. And as well support the creation of the static environment. So for example, new roadworks in the road environments or building quality and so forth. And as well, once we have, let's say, these fundamental benefits in the context of intelligent transportation systems, then we overall improve the environmental perception to support the safety and comfort driving use cases. So what is the current state of ISAC? It is a I2R usage scenario for 6G, and it is also expected functionality since 5G advanced. So 3GPP standards are going to specify ISAC functionality in the next releases. And as we have several work being done by parallel pre-standardization organizations such as FIACIA and other standardization research organizations such as ETSI, which they have an industry specification group. And of course, it's a very hot topic, an active research area in academia and industry. So global activities for ISAC are EU-funded ISAC research direction. So I give an example here from the 6G SNS. We have the Times project, which is focused on industrial scenarios. We also have other initiatives related to for different verticals. For example, we have for e-health, we have for robotics, and we have the 5G ASEA work on ISAC. And then we have the pre-standardization work and, let's say, standardization and research that is being done by ETSI currently on, for example, you can check on this report on use cases and also deployment scenarios, and there are further work that is being done currently now. And here there are other works done by country level research projects such as ICAS for mobility, ComSense 6G. So the problem statement, objectives, and scope for this work item is that we basically, from a really high level, we studied the integration of sensing and communication systems from a C-V2X ecosystem perspective as a high level problem statement. And as I explained before, scope is focused from a communication point of view, in the sense that the sensing functionality is integrated into the 3BP communication system. And objective 1, identify C-V2X use cases realized with ISAC sensing and derive their respective sensing service level requirements. Objective 2, develop an ISAC concept from automotive perspective. So what does it mean, ISAC, from an automotive perspective? This is a very important objective. And objective 3, then analyze the technology features offered by ISAC for the C-V2X ecosystem. So all of these objectives will be, let's say, met with this presentation, with the work that we did in the work item itself. Thank you.
Thank you very much. Now I will call upon David Gonzalez from Contiental to cover the concept that was developed in the 5G work item ISAC. So David, the floor is yours.
Okay, thank you, Maxime. Thank you, Mauricio, for the first part, and good afternoon, good morning, everybody in the call. Thank you for attending. So yes, ISAC is actually a very good technology. Next slide, please. And here we have a first description of the concept we have adopted initially, which is simple, but at the same time broad enough, given the many possibilities and strategies for adoption and implementation. So as you can see, ISAC is something that can be implemented using 3GPP technology, but also non-3GPP technology. And this is something that can be inside the vehicle, which is on board the systems, but also outside the vehicle, for example, based on smart infrastructure and things like that. So the initial focus of ISAC in 5GA is 3GPP technology. And we have mentioned many times that the intention is not by any means to replace current ADAS systems or radars in any short to medium term, but rather complement those systems. Telematic signals will be there anyways, and then extend and enhance the perception of the vehicles and hence improve the safety. Yeah. So as you know, ISAC is a technology that we will have in 5G, hopefully in the next release, and most likely will be something that will be expanded in 6G. Yeah? And finally, I would like to worth mention here that the integration of telematics and ADAS, something called, for example, connected ADAS, is something that has been already been discussed by many important players and was recently presented also in 5GA. This is a very important concept. And it's a very interesting opportunity. But of course, there are a lot of challenges that we will be facing also in next studies, including the technical complexity and feasibility, the cost, the business value for us, for the customers, and also the regulatory compliance and topics like trust and security, which are very complex and difficult ones. So next slide, please. Of course, we have the possibility of having different type of sensing, and now I will try to focus on non-vehicle centric and vehicle centric. And what we could have is, for example, fixed monostatic radar, where we have transmitter and receiver co-located, but we can also have some sort of bi-static and multi-static sensing, where we have transmitter and receiver substantially separated or not co-located. Yeah. So here, a very important aspect I want to to make is that the line of sight component for most of the sensing applications in vehicular scenarios is very important, and most likely in practice we will have that complemented by perhaps other components. Yeah. So in the light of this, we think that the ISAC capable infrastructure, and particularly roadside units, is something that is very important to realize this vision. And in my opinion, it's also very important, not only for ISAC, but for V2X in general as well. Yeah. So another important aspect here that I would like to is that how we are going to share the results or the sensing data from vehicles to the network, and from the network or roadside units or other road users to the vehicles. This is something that has a lot of implications and has been discussed also in other forums, like, for example, in ETSI, how we are going to do that, what are the problems, and it's a very interesting aspect that hopefully will be integrated soon in 3GPP system. So next slide, please. And here is a sort of vision that we have based on what we have today and what we could have in a short to medium term, and also in the medium to long term. Yeah. So as you can see, we can have ISAC not only using 3GPP technology, but many other radio access technologies today, like, for example, Wi-Fi, ultra wideband, and we can have that for in-cabin sensing and also for external sensing. Yeah. So that is more or less the situation. And today, both of these systems, so telematics and ADAS for safety, are more or less operating in a more of independent manner. But in the future, a more level of integration or tighter integration is expected, so we can have more benefits, and we can leverage a little bit more the benefits of this paradigm, hopefully realized by 6G technology. So with that, I complete this part. So next speaker, thank you.
Thank you very much. Jose, it will be back to you. Just a little reminder, please post your questions in the Q&A section of this chat, these questions will be created by the secretariat, and then I will read them out at the end of the presentation. Okay, thanks, Jose. Back to you on the use case and the requirements. Thanks. And you're muted.
Thank you, Maxime. Thank you, David. So yes, going back to use cases and sensing service level requirements, I'm going to basically go through the use cases that we derived in the work item. And basically, usually these use cases have been focused only on the connectivity part. So we realized we did implementation descriptions for the ISAC sensing operation. So we did implementation description for the parking lot management with ISAC sensing operations. So the vehicles are equipped with ISAC sensing or infrastructure. We also, at the beginning of the work item, we derived the use case for ISAC for automated valet parking, in which we went through all the different types of automated valet parking from the ISO standards, and we basically derived the sensing service level requirements from these documents. And as well, going forward, we derived a new use case from a 5GA perspective, is the UE sensing for ADAS. So we have the ISAC sensing functionality within the vehicles that it is used directly for the ADAS functions in the vehicle. ISAC for intersection movement assist. This is let's say a very important use case where, for example, here we show roadside units deployed in order to get into this line of sight scenario that David was talking about, to have a sensing result. And then ISAC for hazard information and road event for autonomous vehicles. So with ISAC sensing operation, collect these hazard information and road events that are occurring on the road and that are a potential hazard. And then ISAC for vulnerable road user detection in intersection. So with these use cases, we basically left you can check that technical report. We derived them in such a way that they are agnostic to the implementation. So you can realize these use cases with infrastructure and or vehicle-based sensing. These are, let's say, the commonalities of these use cases that with different, let's say, implementations, you can, for example, one use case that might be, let's say, in this picture just showed with vehicles, we can also do it with infrastructure-based sensing. And going forward, we also, for each use cases, derived the service level requirements based on standards of the different, for example, automated parking from 3GPP, and also from different technical documents on automotive radar systems. And we basically derived the sensing SLRs per use case in order to, let's say, meet the different requirements that are needed for the particular environment in that use case. And here I'm showing the sensing SLRs per use case, but at the same time, the requirements associated to the reliability of the sensing result, to the latency. You can also find it in the technical report. We will share the link at the end of the presentation. And yes, as I said before, we based ourselves on very good, let's say, discussion and references from automotive radar systems to reach the sensing service level requirements. At the same time, we interacted with 3GPP, so with standardization organization specifying mobile communication, because of their ISAC channel modeling work. So they defined different sensing targets, human outdoor, automotive vehicle, objects creating hazards on roads. And basically we gave some guidance on the physical characteristics of sensing targets that we are expecting in typical automotive scenarios. So this includes motorcycles, e-scooters, bikes, their material, their composition, their shape. And in order to provide some let's say, reference or help the 3GPP study, I then continue this work. Yes, thank you.
Thank you very much, Jose. And now we'll dive more in details into the technology features. And we'll start with David, but followed by Jose. And then I want to introduce also Xuan Wu from Qualcomm Technologies that will also cover these. So I'll let you start, David, first.
All right. Thank you again, Maxime and Mauricio. Okay, let's review a little bit the technology features, which is essentially this slide. But before that, just let me make a comment that, as you see, this is a very promising research and active area at the moment, almost in every important project and research cooperation and pre and standardization. There is a lot of work to do until this is landing into a reality for automotive, but we are committed to progress with that. And this slide, what shows is essentially some of the feature benefits that we see of this technology for automotive. Of course, the most important one is the environmental perception, to go beyond the senses from a car perspective, and some other not so obvious for the users, like, for example, how sensing can improve communication or how communication can improve sensing. And of course, from business perspective, the modularity and potential enhancements in terms of cost reductions. There are, of course, a lot of connections with other complementary technologies which are relevant for ISAC, and here just has a few ones. Some important ones, for example, the concepts for antennas, arrays to steer, directional beams, AIML, of course, and the frequency, what type of frequency is going to use. For example, in automotive radar, this is something that operates in the 70 and 80 gigahertz, yeah, duplex, etc. All these things are tightly connected to ISAC and are things that we are looking forward to continue study within the 5GA. The challenges up to the right there are several ones, and I want just to mention that regulation is one of the important ones, because when it comes to sensing in automotive, it's about safety, and that has particular implications in terms of spectrum, etc. Those aspects has to be considered. As I said, security and trust is always a very deep and difficult discussion. Business model, standardization, data quality, etc. All these are aspects that has to be considered. And on the bottom of the slide, you have a little bit milestones or summarized evolution of ISAC, which is not something new. It was introduced as a concept in the 60s, but it's just recently, relatively recently, that this is becoming a very strong trend being adopted, as it was said, by 3GPP. And now, not only by standardization, but also in pre-standardization, looking forward to 6G, for example, what we are doing also in ETSI. And eventually, at some point, not to speculate now, but eventually, and hopefully we expect this is something that can be adopted and commercialized. So finally, my last comment is, besides of ISAC, in the end of the day, all we do is collect information, store information, transmit information, and process information. From that perspective, we are also trying to look forward what is the relationship between computing in the network and also in the radio interface with this technology. And that is something that I would invite also the audience to have a look to ETSI, where we are working on those aspects, and hopefully we will introduce these elements also in the 5GA work. So with that, I conclude my part, and I'm back to Maxime.
I'll hand over directly to Jose. Jose, and you're muted.
I hand over to Xuan.
Okay.
Sorry about this. Xuan.
Thank you, Maxime. Thank you, everyone. So, yeah, in this slide, we will talk about some technical considerations for ISAC, and in particular, mechanisms that can reduce resource consumption for ISAC operation, or for the sensing operation in particular. So in some earlier slides, Jose talked about the automotive use cases, and as we noticed, for some of them, the requirement are actually quite stringent in terms of the sensing KPIs. And generally speaking, those sensing requirements will be translated to radio resource requirement. And if we're talking about integrated system, or if we enable the sensing operation in the communication system, then the resource efficiency or the resource consumption by sensing becomes a concern, right? So now on this slide, basically we are talking about maybe two mechanisms. So on the left of the slides, we're talking about this spatial multiplexing of the sensing signal transmission and communication signal transmission. This is feasible in the automotive context because maybe if we think about sensing in the automotive context, mostly it's about detecting objects surrounding the vehicle. So that basically means for the sensing operation, maybe when the vehicle is a transmitter of the sensing signal, the transmission will not have an elevation, right? Or in other words, it has a 0-degree elevation for the purpose to measure the vehicle surroundings. But if we look at the communication, in order for the signal to reach the base station, maybe the communication signal would have a positive elevation. This basically allows the multiplexing of sensing and communication signal transmission. So let's see, one UE is using this resource for the communication signal transmission to the base station, and then another UE can use the same resource for sensing. Hopefully, this would significantly reduce the resource consumption for sensor operation in the communication system. The other mechanism we're talking about here on this slide is on this right-hand side of this figure is multi-stage sensing. So this also has to do with sensing requirements or the KPI, right? So as we said, for those KPIs, it will be translated to the resource requirement. And for some of them, maybe let's see, you will need a lot of resource, for example, to measure the velocity, right? So, and then if we just follow a conventional sensing approach, that basically means that the transmitter needs to do this always on transmission of the sensing signal. Because if we compare the sensing and positioning, maybe one significant difference is that for positioning, we know that there is a UE over there, but we don't know its location. So we need to position that UE. We know that there is already a UE there, right? But for sensing, it's different, because when you do sensing, maybe you don't even know whether there is a target over there or not. So that basically means that if we follow a conventional sensor approach, the sensing signal transmission needs to be always on, because you always need to determine, to detect if there is an object. And then with this multi-stage sensing, so let's take 2 stages as an example, right? In the first stage, maybe the transmitter can just transmit a sensing signal with a wider beam using less resource, basically just to determine or to detect the presence of the target. And if the presence of the target is determined from this first stage sensing, then the second stage sensing can be triggered. And in this second stage sensing, the transmitter can transmit maybe using a narrower beam and transmitting in a wider bandwidth, in a longer duration, basically to meet the sensing KPI requirement. So these are the 2 considerations at the very high level, and hopefully with this, we can reduce the resource consumption for sensing, especially if the sensing and communication are shared the same spectrum. And at least technically, this would make maybe adding the sensing function to the communication system kind of sustainable. So that concludes this slide. Thank you.
Thank you. Jose, I guess.
Yes. Thank you. Yes, so thank you, Xuan, for the nice technical considerations on ISAC for automotive. So now one important aspect is the level of integration that we have between the sensing and communication system, which is very relevant for some of the benefits that David explained. And we identified in this work item 4 different levels that are relevant for the automotive ecosystem. And the first one, or let's say the less integration, let's say, between both systems is the higher layer integration. So both systems operate at different bands, and they are also, let's say, implemented in different hardware. And here, okay, there's no potential for hardware reuse, but the sensing system can readily share information to the communication system in order, for example, to improve communication functions, so beamforming, some fast handover operations, and so forth. And as well, the communication system can readily provide communication services to different sensing systems in order to do this communication assistant sensing. So that means multi-static sensing, have sensor fusion from different sensors readily done by this higher layer integration with the communication system. And this is the one that has no hardware reuse. If we go further, the benefits of hardware reuse improve. So the next one is spectrum level integration. We have different systems that have a shared band. So we are not using the same hardware for both systems, but they anyways use the same frequency band. And this level of hardware reuse can, for example, allow for the reuse of RF components. And this is because they're, of course, if you're using the same frequency band, then both systems can use the same RF chains and antennas. But since you don't have this high, let's say, integration at the hardware level, then there are some constraints that you have in order to multiplex both signals. And one of them that you could do is to multiplex the sensing operation in the time domain, and then with the communication signal. So do them interleaved, do both functions interleaved in the time domain. Then going further in the integration levels, we have the hardware level integration, in which we have the same system. So both are implementing the same hardware, but they are using different bands. So here, yes, we have an increased level of hardware reuse. So for example, the baseband can be reused for both operations. And we basically, for example, could use a licensed frequency band for communication that is typically used for C-V2X, for example, in the ITS band. And then for the sensing operation, we could use another frequency band, for example, a frequency band that is currently used for automotive radar, 77 gigahertz, while reusing hardware components. So this is one, another, let's say, level of integration that we can have. And this, as we have the analysis we have done, it wouldn't have impact on the standards as per the studies that we have done within the work item. Then on the full integration is we have the same system with the same band. So this is like, let's say, the one that maximizes the hardware reuse, because we're using the same antenna, same RF components, and same baseband. And this basically is let's say the most beneficial in terms of sustainability and also flexibility, because since we are reusing both the hardware and frequency band, the main benefit from this integration comes from using the same hardware, in the sense that we can have this flexibility of, let's say, allocating resources in the time frequency or space domain for the sensing operation and the communication operation. So from a communication system perspective, it would be obvious to, for example, use the already existing waveforms, for example, OFDM, where sensing signals could be specified as a reference signal or as dynamically assigned by the system. So depending on your sensing requirements, then the system can allow for an increased number of subcarriers in order to reach some level of sensing resolution, or allocate the resources in some other way based on the communication requirements and also the sensing requirements. So this is the level of integration that offers both flexibility and also maximizes the hardware reuse. So we envision this is a very attractive integration, because it offers benefits in terms of, let's say, reduce space, reduce costs, and also potentially also improve more the communication performance, as well as flexibility to reach the sensing level requirements that we have in automotive. So yes, these are very, let's say, high level integration levels that we, let's say, discussed during the work item, and this required further work to really understand the details on the implementation complexity, on the performance, on the different benefits, cost benefits of using different frequency bands, levels of integration. And this is something that we are planning to continue working. And now, exactly, as I just said, these are the pending challenges that we have. And as also Shanshuan mentioned, also, if we have this level of integration, this full integration, then it is something, let's say, a requirement is that we minimize the sensing resource consumption that we have, because we would reuse the same resources. And given that the nature of communication it's mostly driven by random traffic patterns from the different users, but in sensing we can have a more, let's say, deterministic, well, not deterministic, but let's say more predictable behavior of the sensing resource, because we could periodically send some signals in order to do environmental perception, whereas communication will be driven by the application layer demands from the users nearby and also in the network. So these are the different ISAC integration levels, and yes, this is further discussions, further analysis that we are doing in order to understand what are the different benefits from an automotive perspective.
Thank you, Jose. I'll give you a few minutes to conclude, and then we'll pass to the Q&A. There are a few questions already posted on the Q&A panel. You can also vote yourself whether there are some questions that are more suited, and don't hesitate to just support me in prioritizing the questions. So Jose, conclusions. Thanks.
Thank you, Maxime. Yes, so the key takeaways that we have derived in this initial work from ISAC, we introduced this topic to the 5GA. It was new. And the key takeaways is that we have the first ISAC use cases and requirements that we developed. We envision that we just touched the first use cases that we can realize with ISAC. But however, there are several other use cases that are facilitated by ISAC. And then we have the concept that we have. So we expect that we will have a gradual adoption of these systems towards 5G advanced 6G, vehicle-based and infrastructure-based ISAC sensing. And the features for automotive is, okay, one opportunity that we have is that ISAC provides the potential to reduce costs for OEMs, for example, car OEMs. And we have to further, let's say, there are several new business possible opportunities for the MNOs, for the OEMs to realize C-V2X 5GA use cases that we have already talked in 5GA. And then the challenge now is as an ecosystem to really discuss together. For the C-V2X ecosystem, we need to really understand from a holistic point of view all the different aspects related to implementation, so levels of integration, frequency bands, but also regulation, trust of the sensing result derived from an ISAC system, and many other implementation aspects that need further discussion. So that's why we in 5GA, we have further steps for ISAC. We are analyzing this work further. So we are doing a further study of implementation of ISAC for automotive. We're doing a value assessment and business opportunities for the ecosystem and also from a stakeholder perspective. And we have the evaluation of existing ISAC channel models. This is work that was done by 3GPP. So we are assessing the validity, applicability of those models for automotive. So with that, these are the key takeaways of the initial work that we have done on ISAC in 5GA, and we have plenty of work to be done, and that's why we are, let's say, further discussing within 5GA. Thank you.
Thank you very much, Jose. I will pass to the Q&A. We have quite some questions already on the tool here. You can also mark your support for these questions. Perhaps I would like to come first to the relation between 5GA and 3GPP, because quite a lot of this is being done at 3GPP level. What are the relations, or how do you interact, and who are the main players in terms of standardization of ISAC in 3GPP? Thanks. Who wants to take the floor? Jose.
So, Maxime, if I understood correctly, so the main players from 3GPP, so from ISAC, could you repeat the question again? Sorry.
Yeah, the question is how is 5GA actually liaising or exchanging your results to 3GPP, and eventually how the results are used in 3GPP for standardization? Thanks.
Yes, this is a very good question. So, as 5GA, what we do is that usually the procedure would be that within a work item, we perform different discussions, and then for some specific point that we want to communicate to 3GPP, then we reach consensus on some point from the different view of the different companies, and then together we create a liaison statement to interact with 3GPP. So we have a liaison statement officer in our case, because we have 3GPP delegates within the work item. And basically, they are the ones, let's say, presenting this contribution in a 3GPP meeting. And this, let's say, this contribution can be adopted by 3GPP for some guidance or for some, let's say, contribution.
Thank you, Jose. David, you have a raised hand. Can we a short one? Because there are quite many questions.
Yes. So fundamentally, Maxime, as mentioned, some of the people in 5GA, we are also participating in other standardization, and we provide inputs and requirements. For example, characterization of the targets which are relevant for automotive scenarios and certain values. And we are also taking now outputs from 3GPP, and I'm going to evaluate, for example, the channel model in simulations which are important for automotive. This is just one example of how we are interacting, and of course we follow very closely all the progress there. Yeah.
Great, thank you. So there are a few more questions here related to the spectrum, and in the presentations you very little talked about what kind of spectrums we are considering. Especially one of the question is related to the 5.9 gigahertz, asking whether this 5.9 gigahertz band is suitable for the sensing, as this is quite narrow band kind of bands here. We are talking about 10 or 20 megahertz. What is your take there? Thanks. Thanks.
Yeah, maybe I'm going to start, and maybe David can refine the answer. Yes, so basically, since yes, we have this narrow spectrum in 5.9 gigahertz, as we have seen the sensing requirements, there are different communication license frequency bands that could be used for the sensing operation in order to have enough bandwidth. So, for example, we have one example could be a millimeter wave, which has, as of now, a significant amount of bandwidth in order to meet sensing requirements. There are other options as well. And I leave the floor to David if he wants to add further comments.
So just a small compliment. So here you have to, for example, understand that automotive radar start at 27 gigahertz, and nowadays most of commercial systems operating above 71. So that tells you what is working and what is not working when it comes to sensing because of the resolution. Yeah. Besides that, it is important to understand that the sensing spectrum has a very strong regulation because it's related to safety, and no communication is foreseen in any close future. So communication system cannot jump on top, but we can have sensing in the spectrum used for mobile broadband like 3GPP. In the end, if we adopt that, the initial statement is that whatever we use as a complement to safety or ADAS cannot make what we have already worse by any means. It should only help and complement in a positive manner. And obviously the spectrum that is more treatable in our opinion is a spectrum in the millimeter wave spectrum for many physical reasons. Yeah.
Thank you. Actually, at least in Europe, there is a spectrum for ITS that is allocated already at a 60 gigahertz band. I don't know of any organizations that has really fully considered these for implementations, but perhaps this is open door for ISAC in the future. Now, but a side question to this is. To what extent are we considering radio to do sensing, or the opposite, radars or sensors to do the communication? And what is meant here is that radars could also become communication devices in the future. So is there a sense of what is most appropriate in the future?
So definitely one of the things that we explained at the beginning of our work item. So from a future point of view, it is much more feasible to integrate the sensing onto the communication, because if we do the other way around, we have limited, let's say, using the same waveforms for sensing, for communication, or something in that direction, the communication performance that we can achieve is not would not be, let's say, suitable. So from a C-V2X centric point of view, that's why in the work item, and also most of the industry is focused the other way around, integrated sensing functionality into communication systems.
Okay, that's a good answer. Thanks. There, I'm going to read another question that's related to the service level requirements. So basically, for use case like hazard information or road events, what is the expectations in terms of delay or latency of the sensing? Is it realistic to assume that sensing performed by 3GPP RAN nodes, followed by processing and transport of the sensing data, can all be completed in time to alert a user of a vulnerable road user? So basically, are we confident that we are going to sense this in time with these ISAC functionalities? Thanks.
So I will start, and perhaps David will complement. Yeah, the physical layer from communication systems is already, let's say, operates at a very granular level, at millisecond level. We do many channel estimation functions, everything extremely quickly optimized for the best way possible. And the different hubs that we will have in order to reach the requirement is definitely, from my point of view, achievable. And we have a 100 millisecond latency, if I recall correctly from the technical report, for those type of use case. Maybe David wants to add something.
Yes. So, Maxime, I can say that actually there are many interesting questions. We are not going to cover all, but related to this one, which is also a good one. My take here is that meeting for example, the latency between data acquisition, round trip back to actuators, should be something for real-time type of safety vulnerable road users. It should be in the order of 200, 300 milliseconds. That is something that is feasible. A major obstacle here is in the direction of robustness and notions which are connected to functional safety. For sensing, we also need that, same as for communication. And that would be the aspect that has to be studied and considered more carefully from 3GPP perspective if they want to introduce and be successful with ISAC in automotive.
Thank you. Thank you. I'll take another question here. When is ISAC expected to be commercialized? Is there a time frame for its deployment? And perhaps a side question to this, when are we going to see this fully standardized also in 3GPP? Thanks.
If I can, so just to give a reference, so for example, in 5G Advanced, they will continue with the normative phase of ISAC focused on network-based sensing. It means that locally in 1 year, 2 years, 1 release or 2 releases, we will have this ISAC functionality for network-based sensing. Obviously, for automotive, the most relevant part is the UE-based sensing. Yeah, how UE performs sensing. And this is something that at least will be considered from a starting point, most likely in 6G. So you make the numbers 2030, 5 more years. So probably that tells you when we are realistically adopting this technology. But there is a lot of work to do. So yeah, it's okay.
Thank you. Thank you. And knowing that we are talking about at least 3 to 4 years adoption between standardization and then the time it gets to in the automotive products, then we have more or less a time frame here. There was also a second question in that, and I'm trying to find it again, but so the question is basically, how do you see this evolving in terms of complementarity or replacement of some of the current sensors? In the picture that David showed, it seemed that everything would become ISAC, but nowadays we see a very large amounts of sensors on the vehicles. Do you really think that it's feasible that we are ending up only with ISAC sensors, or the sensors are still going to be there for a long time? Thanks.
So here, just quick, ISAC doesn't mean we are going to replace any sensor or that we have to live with one type of sensor. It's a concept that actually integrates different type of sources and make them interoperable. So that is fundamentally the answer for that. So it's not about replacing anything. It's a very broad concept, yeah, as it was mentioned.
Thanks for being short. There are a few questions flowing in the meanwhile. There is a question about the ISAC channel model in 3GPP RAN 1. Do you have intentions to also consider other channel models in your studies? Thanks.
Maxime, at least we are going to consider the 3GPP model, which is just released in RAN 1, and hopefully we can consider some additional features which are developed by EXI, the Industrial Study Group on ISAC. At least these two things are something that is in scope. It's fine for Mauricio. Thank you.
Okay, good. Thanks. There was a question really at the bottom here about the backward compatibility of the roadside units that are already installed, and eventually how they can use ISAC. There is this even what would be the incentive for the owner of roadside unit to incorporate ISAC? Will the existing roadside unit be upgradable? I don't know if you can answer this shortly. Thanks.
I would say very shortly, it really depends on the level of integration that we have, and also if this integration makes sense from an implementation perspective. That's why we have the further work in 5G to really understand the implementation complexity, what are the implications for current deployed equipment and future ones. So yeah, this for further study, the answer.
Thank you. Looking at the questions, the commercialization. So I have another one. What is the role of V2N in ISAC? That's okay. I thought that it was clear. And how does this compare with the V2I, so the V2 and the V2V? For example, does V2N signal have a role in the sensing aspects itself? I think it was clear even from your introduction, but perhaps you can complement. Thanks.
Mm-hmm. So here, very concisely, Maxime, it has to do with the time scale of the sensing applications. Of course, for something where you need to react faster, V2I/edge computing type of is suitable. V2N is for something that has a different time scales. Yeah, and related to the previous one, which is one of the best ones, the motivation for the roadside units vendors. There is no strong business behind safety applications, so that is one of the points that has to be studied and analyzed. Perhaps regulation will help here.
Okay, more questions flowing. For full integration, how do you envision that regulations will need to change?
So far we have the license band for communication, and we already do some sort of angle of arrival estimation with pilots that are sent in the communication system. So this is some sort of sensing already. And further work has to be done from a regulatory point of view to really understand if there has to be an explicit change of regulation. But most likely this is, perhaps it will, and this is something that we are further discussing with the other 5G members in the team.
Thanks. I think we'll come to the end here of the webinar. I would like to really thank the panelists for really putting this difficult topic in a layman's form for all of us. And really, you can continue the discussion with the authors of the report. They are listed here. Don't hesitate to reach out to them. And in the meanwhile, I wish you a very good summer period to all of you, and have a good evening then. Thank you very much.
Thank you.